sklearnensembleRandomForestClassifier. Description: the random forest classifier is an ensemble learning method for classification tasks that operates by constructing a multitude of decision trees during training and outputting the class. That is, the mode of the class is classification or mean average prediction regression of pay. Individual trees. Inputs. X the training input samples. This should be a 2D array, where each row represents a sample and each column represents a feature. Y the target output values. This should be a 1D array, where each element represents the class label of the corresponding input sample. Outputs. The trained random forest classifier model. The predicted class labels for new input samples. Steps. 1. Bootstrap aggregating. Bagging. The random forest classifier uses bootstrap aggregating, which involves creating multiple subsets of the training data by sampling with replacement. Each subset is called a bootstrap sample. 2. Decision tree construction. For each bootstrap sample, a decision tree is constructed. However, instead of considering all features at each split node, the algorithm randomly selects a subset of features, usually the square root of the total number of features for classification. 3. Prediction. To make predictions for new input samples, the random forest classifier combines the predictions of all individual decision trees. In classification, the most common class label predicted by the trees is chosen as the final prediction. In regression, the average prediction of the trees is taken as the final prediction. Metrics. Accuracy. The percentage of correctly classified samples. Precision. The ratio of correctly predicted positive samples to the total number of predicted positive samples. Recall. The ratio of correctly predicted positive samples to the total number of actual positive samples. F1 score. The harmonic mean of precision and recall. AUC area under the curve. A measure of the model's ability to distinguish between positive and negative samples. Visualization plots. Feature importance plot. This plot shows the importance of each feature in the model. Decision tree visualization. Visualizing individual decision trees within the forest provides insight into the decision process. Confusion matrix. This matrix displays the number of true positives, true negatives, false positives, and false negatives. Fine-tune parameters. Nestimators. The number of decision trees in the forest. Increasing this number typically improves model performance but also increases training time. Max depth. The maximum depth of each decision tree. Limiting this depth can help prevent overfitting. Minsamples split. The minimum number of samples required to split an internal node. Minsamples leaf. The minimum number of samples required to be at a leaf node. Max features. The number of features to consider when looking for the best split at each node. Bootstrap. Whether to use bootstrap aggregating when creating the bootstrap samples. Criterion. The function to measure the quality of a split. Uncertainty methods. Out of bag OOB score. This score is calculated using the samples that were not included in pay. Bootstrap sample for each tree. It provides an estimate of the model's generalization performance. Confidence intervals. Confidence intervals can be calculated for the predicted class probabilities. Challenges and fixes. Challenge 1. Overfitting. Random forests can overfit the training data if the number of trees is too large or if the trees are allowed to grow too deep. Sample use case. A model trained on a small dataset with a large number of trees in a deep max depth might overfit and perform poorly on unseen data. Fixes. Reduce the number of trees. Nestimators experiment with decreasing the number of trees to prevent the model from becoming too complex. Limit the maximum depth of the trees. Max depth. Setting a reasonable maximum depth helps to Prevent individual trees from becoming too specific to the training data. Use early stopping. Monitor the performance of the model on a validation set during training and stop training when performance on the validation set starts to decline. Challenge. Too high variance random forests can be sensitive to the specific training data, leading to high variance in the predictions. Sample use case. A model trained on a dataset with a few outliers might be heavily influenced by those outliers, leading to inaccurate predictions for new samples. Fixes. Increase the number of trees. Estimators. A larger number of trees can help to reduce the impact of individual outliers. Increase the minimum number of samples required to split a node. Min samples split. This helps to prevent the trees from becoming too sensitive to individual data points. Use bagging. Bootstrap aggregating can help to reduce variance by averaging the predictions of multiple trees trained on different subsets of the data. Challenge 3. Interpretability. Random forests are often considered black boxes because they are difficult to interpret. Sample use case. Understanding why a specific prediction was made can be challenging due to the complexity of the ensemble of decision trees. Fixes. Feature importance analysis. Examining the feature importance scores can provide insights into which features are most influential in the model's predictions. Partial dependence plots. These plots can visualize the relationship between a specific feature and the model's output. Sharp values. These values provide an explanation of how each feature contributes to the prediction for a given instance.